Now we're ready to look at converting other normal distributions to the standard normal distribution. So let me just go right to an example, and hopefully you're kind of seeing the connection before we even start to go through this. But we have an American adult male is randomly selected. American men have a distribution of heights that is approximately normal, with a mean of 70 inches and a standard deviation of 3 inches. So I wrote that information down. I also know, because the distribution is approximately normal, I can start to draw my picture right away. I have a bell-shaped curve because of it being a normal distribution. Now the standard normal distribution is centered at 0. Our distribution is centered at 70. We also remember that that graph has a concave up, concave down, concave up feature, and that spot that where the concavity changes is called that inflection point, and that is one standard deviation away from the mean. So if I back up to this point, since my standard deviation is 3 for heights, I know I need to mark that as 67 inches. And then I went back another standard deviation, or 3 inches, to 64. And so I'm marking out 3 standard deviations to the left, and I'm also going out 3 standard deviations to the right. This score should have a z-score of 0. This score of 73 inches should have a z-score of 1. 76 should be a z-score of 2, and so on. 68% of our data should be approximately between these two numbers. 95% of our people should be between approximately 64 and 76 inches. And we would have 99.7% of our people would be between 61 inches, 5'1", and 79 inches, which would be 6'7". Now, we worked with the standard normal distribution in calculations, and now we're going to work with the regular normal distribution. I want you to write these things out basically the way I'm showing. So it's the way you write it is not quite as important, but the idea behind it is the most crucial thing. But the way you write it out is going to be graded as well as being able to be accurate. So I want to find what's the likelihood if you randomly choose a man that his height is less than 67 inches. And we can see 67 inches is right here. We could even look at this chart knowing that 66 inches, I think I just said 67, but 66 inches is right here. We know 67 is a negative 1 z-value. We know 64 is a negative 2 z-value. So we could actually look at this and figure out what that z-value is just by doing some proportional reasoning. But initially, our distribution, we're finding the probability that x, which I'm letting stand for the man's height, is less than 66 inches. We need to now convert that to a z-value. So now this variable was just x, standing for height. Now we're going to the standard normal distribution, and we remember how we calculate our z-value. The score we have minus the mean divided by the standard deviation. And now I have the probability of z being less than negative 1.33. This is just like we did yesterday. We now would go to the standard normal distribution, and we want to find this area down here for being below negative 1.33. So we would take our chart, we would go to negative 1.3, column of 03, and find the intersection of those two and find it to be 0.0918. So the probability of randomly selecting a male and having his height be less than 66 inches tall, or 5'6", if these two are true, is about 9%. Now let's, on the other hand, part B, find the probability that a man is randomly chosen and he's higher than 6'8". 6'8" is 80 inches. So I start out, write my probability statement. Don't use a z here because this right now is not a z-score. It's a score that stands for the height of a man. We need to convert that to a z-value. The score minus the mean divided by the standard deviation. And we can see up here, if we go to 80 inches, that that z-score is going to be higher than 1, 2, 3. It's going to be 3 1/3. And when we do the calculation, we get 3 1/3. We will need a 2-place decimal because that's the way our table is looked up. And now, remember what happens if I look up 3.33. If I take this chart and look up 3.3 and go to the 03 column, I get 0.9996. But that's the area that is below 3.33, and we want up above. So 1 minus the 0.9996 gives me this value. I could also use symmetry, and the area that is above 3.33 would also be the same as the area below negative 3.33. And negative 3.33 will give me that area of 0.004 directly. So I can utilize some symmetry. So once we write our statement and convert it to the z-value, it is truthfully the same as what we did yesterday. Find the likelihood of randomly choosing a man and having his height be between 64 inches and 74 inches. I look at my chart, 64 inches, I can see that's going to be a z-value of negative 2. 74 inches is up here, so I know I'm looking at between this value and this value and finding that shaded region between. So I write my statement down. I convert each of these scores to a z-value, which this one, again, I could pick right off my graph, as I could this one because of the way I scaled it very nicely. And now I have to find the area below negative 1.33 and find the area below negative 2. And that difference will find the area between. Okay, so once we do our conversions, we have exactly the same calculations we did yesterday. Now, relate this to what we also did yesterday. I want to find 90% of men are shorter than what height? So another way to word that is I want to find the 90th percentile. So I like to draw myself a little picture and then also kind of explain what I'm trying to find. So I have my little picture. That's what I'm looking at. I want the area, and here is that 70 inches right here in the center. And I want to find the score that has 90% of the heights less than or equal to it. And that's what my statement says here. Now, I need to find this z-value. That's an area. I need to find that z-value. And remember, in our chart, flip it this way, in our chart, inside these 4-digit numbers, these are areas and probabilities. So I would need to look around here for 0.9. And when I would go along, I see a 0.932 here. Go over to this column and back it up, and I say, ooh, there's a close one. 0.8997. That's only 3/10,000ths away. That's really, really close. And that corresponds with a z-value of 1.28. So this score is 1.28 standard deviations higher than the mean. There's my z-score formula. Plug in what I know. I know this value. I know the mean. I know the standard deviation. And I do a little algebra. Multiply both sides by 3 and add on 70. And I find out that the score of 73.84 inches, anyone who is 73.84 inches, or approximately 74 inches tall, 6'2", is basically in the 90th percentile. A couple more things just to look at we worked with this same idea yesterday, but I want you to see the difference between a percentile question and a symmetrical range. All right, so now we're going to find the symmetrical range, which includes 90% of the heights and 95% of the heights. So now symmetrical range, my picture is different. I have the area between my numbers, and that's not a very good normal distribution curve, but the area between my numbers symmetrically has an area of 0.9. So there are two scores I have to find here, and we know that the center is at 70 inches. I need to know how many standard deviations away to go. And remember, if I have an area underneath the whole curve of 1, I'm missing 10%, so 0.05 or 5% has to be down here, 5% has to be up there. I need to find that z-value and that z-value, and they're just opposites. So I wrote my picture. I wrote my question down. I know these values are symmetrically located about 70 inches, and the z-values will be symmetrically located about 0. And that's that one that's right halfway between. A z-value of negative 1.64 is 0.0505, and a z-value of negative 1.65 is 0.0495. So right dead set in between is the value we want. So those are our two z-scores. One of them is positive, one of them is negative. I can set up two separate equations for this, or I can kind of do the little plus or minus and kind of figure it out. And once we do that, we find out, and sorry about the little marker there, but once we do that, we find out that this one value is about 65.1 inches and 74.9 inches, that if we have 90% of our males will be between those two heights. And then notice what would happen if we want to change the question to be a 95% of the heights are in between what two values. Our picture would change. And now 95% are between these two, so we're missing 5%. 5%, 0.05 divided by 2. Each of these little tails will have an area of 0.025. And if I go to 0.025 for an area, well, I'll get that right away. If I look up an area of 0.025, and I'm getting pretty close to one here, 0.025, and I find that it is closest to, and you look for it, 0.0256. Oh boy, look at that. It's like right dead on. Negative 1.96. Aren't many times we have that exact value in there. But I have this value is negative 1.96, this one's positive 1.96, and I do exactly the same calculation to converge. So we would say that the symmetrical range that includes 95% of the heights is between 64.1 about and about 75.9 inches. Okay. And now it's ready for you to practice on some normal distributions.